Break a leg, man.
Oh, Keith, who's doing the introduction? Is it you or Tim? Are you?
Uh,
Okay.
All right, we're just going to give people a few minutes to filter in, and then we'll get started with today's talk. All right, well, hello and welcome everyone to today's CIC Virtual. Today for CIC Talks, we're welcoming Dr. Phil DeLuna from the National Research Council of Canada. My name is Keith Lapierre, and I am a program coordinator at the CIC National Office, and I'll be your host today. So this series of CIC Talks is brought to you by the members of the Chemical Institute of Canada. The CIC works to connect the Canadian chemical sciences community through our constituent societies. CIC Talks are a series of virtual discussions amplifying the fantastic work that goes on throughout our chemical sciences community, is doing to tackle global issues from teaching online to today's topic, self-driving labs for materials discovery. And while we can't meet physically, we hope that this new series really helps to enable the Canadian community to stay connected. So as I mentioned before, we're excited to welcome Dr. Phil DeLuna from the National Research Council of Canada, where he serves as a program director for the Materials for Clean Fuels Challenge program, leading a multidisciplinary collaborative 7-year, $57 million research project to develop made in Canada novel materials to produce clean and sustainable energy. Phil received his PhD in material science and engineering, from the University of Toronto in 2018, and has been a visiting scholar at Stanford, UC Berkeley, the Lawrence Berkeley National Lab, and the Canadian Light Source. Phil was one of 10 finalists worldwide in the $20 million Carbon X Prize and one of 20 semifinalists worldwide in the $7 million OCE Solution 2030 Challenge. Phil was named in the 2019 Forbes Top 20 Under 30 Energy List, 2019 Green Biz Top 30 Under 30 list, and is a Governor General Gold Medalist. So without any further delay, please join me in virtually welcoming Dr. Phil DeLuna. And with that, Phil, I will kindly ask you to start maybe sharing your screen and we can dive right into your fantastic talk for today.
Perfect, thank you so much. Thanks, Keith. So I'm just gonna share my screen here and then get started. First, I just wanted to thank Keith and CIC and Tim and everyone for allowing me the opportunity to speak. I'm gonna dive right into this and give a little bit of a talk today around what the future of self-driving labs for materials discovery looks like, and automation and artificial intelligence and robotics, and how they can be used to help accelerate discovery. But before I do that, I want to, of course, give my spiel on what the NRC is and what we do. So the National Research Council of Canada is Canada's chief research and technology organization. We employ around 4,000 scientists, engineers, and other specialists in 22 national labs across the country. We have a presence in every single province and I think almost every single territory. And these are outdated numbers, but in 2018, we spent a little over $1 billion in research. We've been around for quite some time, over 100 years. And really, we're here to respond to what Canada's needs are from the perspective of science and technology development. Whether that be in our founding days, where it was about nation building and responding to world wars. A lot of the work that we did also underpinned some of our defense work, or whether that extended into the space race. A little known fact about the NRC is that the Canadian Space Agency actually spun out of the NRC. So some of the first astronauts that Canada has ever seen were a part of the NRC. Over time, NRC started responding by providing research support and funding to small medium enterprises through its Industrial Research Assistance Program, or IRAP. And we actually have a long history of funding research. The Natural Sciences and Engineering Research Council, or NSERC, which funds the majority of all of academic research in Canada, actually spun out of the NRC as well. And most recently, we've been thinking about what are the biggest things that face Canada. And even more recently, we've been working very hard on technologies to respond to the pandemic, whether that be developing new vaccines or helping to scale up our facilities for vaccine production in Canada, or whether that's new technologies for contact tracing, et cetera. But even beyond COVID-19, I think one of the biggest challenges that Canada and really the world faces is climate change. And that's a topic that I'm very passionate about. And I wanted to preface this talk about self-driving labs by give an understanding of why we need them and sort of the challenges that we face and how they can help to address some of these topics that you see on the screen. My program, the Materials for Clean Fuels Challenge program, is focused on trying to decrease Canada's emissions, its GHG emissions year over year. So what's really interesting about Canada's GHG emissions is if you break it down by sector, waste, agriculture, buildings, transportation, electricity, you can see that a lot of them are going down. Electricity is decreasing by a lot, as seen in green here, because we're outphasing coal, and Canada is blessed in being such a large country with an abundance of natural resources to have access to a lot of hydroelectricity, a lot of renewable electricity. The two sectors, though, where we're actually increasing GHG emissions are manufacturing and petrochemical and oil and gas. And there are really two kind of drivers to this increase. One, the world population is increasing, and two, quality of life, especially in developing economies, is increasing. So Canada's energy products are becoming more and more in demand worldwide, and that increase in GHG emissions is because of the absolute volume or value of GHG or production of energy products that Canada has. While in fact, we're actually becoming more and more efficient from a per capita basis on decreasing our GHG emissions per person, it doesn't keep up with the pace at which we're producing energy products. And we really need to tackle these kinds of sectors. Canada has made a target in 2050, which has evolved over time, to be net neutral. And in 2007, the idea was to have 65% GHG emission reduction by 2050. And that was a target set by the federal government in 2007. In 2016, that target increased to 80%. And just this last year, after the previous election, there was a commitment from the federal government to reach 100% GHG emission reduction by 2050 in relation to industrial targets, or the Industrial Revolution setting. And we're not alone in the world in our desire to become net neutral and our desire to limit and decrease our GHG emission reduction spending. For an example, just in June, two large announcements. Germany announced $9 billion in long-term renewable energy storage, or energy strategy, sorry, I should say, energy or hydrogen really as the vector for their clean recovery. And in the UK, they announced that $100 million for innovation in CO2 direct air capture. So if we look at the pathways to decarbonize Canada, we can kind of break them up in a few ways. The first, in the green, are technologies that kind of exist today but need to scale. So solar cells, batteries, things that we have technology for but still need to be implemented more widely. In blue, those two wedges there that account for almost half of the emission reductions that we need are technologies that we do not yet have or are at an early stage, such as zero emission transportation fuels and the decarbonization of industrial processes. So my program is focused on addressing these two sectors because we need advancements in this, especially, and we need those advancements right away. And so this is the vision that my program has and that I have for a renewably powered chemicals and fuels industry, where we can capture carbon dioxide from the air or from a flue stack from an industrial emission power plant, and then convert that using renewable electricity and water into decarbonized industrial chemicals or net zero emission transportation fuels. What we're essentially doing here is bypassing nature in a way. I like to think of hydrocarbons and fossil fuels as essentially liquefied sunlight that has over a millennia or more condensed underground and turned into liquid form, which we then extract and get the energy from. Now imagine instead of having to wait that time and all that pressure, if we could capture CO2 directly from the air and then use renewable electricity like solar, wind, hydro, and convert that directly into chemicals and fuels that we need. The point of this is really to tackle the sectors of the economy and of the world that are very difficult to decarbonize with electricity alone, these hard to abate sectors. And at the core of this technology, what underpins all of this is transformation and a step change. It's sort of the materials that enable the transformation of CO2, water, and electricity into chemicals and fuels. And so that's what my program is focused on. It's a 7-year, $57 million collaborative program where we're working with academics and startup companies in Canada, Germany, the UK, and the US, along 3 main thrusts: materials for CO2 conversion, hydrogen production, and AI for materials discovery. And that AI for materials discovery is the basis of which this talk is about today, and how I like to think about self-driving labs for the future. So first, I'm going to start this off by asking, what is discovery? And how long does it take to go from a discovery to a product to impact? Now, what you'll see here, this is a very common graph that economists and technology developers have used and to explain the valley of death. Essentially, the cost it takes to develop something and move from a discovery to profit. On the left-hand side, we start with a discovery in the lab, a eureka moment. And what people don't realize is that over time, it can take up to years, especially in a hard science and in something where you're making things or manufacturing things. It can take years to go from discovery to development to prototype to demonstration, etc. And the cost at which to do so is really exponential. Something that costs maybe $100 at the discovery level will cost $1,000 at the development level, will cost tens of thousands of dollars at the prototype level, and hundreds of thousands of dollars at the demonstration level, especially if it's something that has to do with clean energy. And so what's interesting here is that their digital technologies, that gap in terms of the cost and the valley of death is much lower because the capital expenditure is much lower. This essentially means that if we can leverage digital technologies, artificial intelligence, et cetera, to help accelerate and move that valley of death higher, then we have a chance of potentially being able to decrease the time it takes to go from discovery to development. And so how long does this actually take? What does this mean? What you're seeing on the screen here is a study that was done in 2018 in the energy policy paper that wanted to really look at the time it took for invention, development, and demonstration to market deployment and commercialization. And they're grouped at the bottom of the axis here is time, anything from 1880 to today. And at the very top, it's novel products for new markets. So the first thing on there is the car. Well, it took what, about maybe 20, 30 years for development, initial invention, development, and demonstration, and then another 30 or 40 years for that to be widespread. As time moves on, consumer-facing products like the cathode ray TV, the video cassette, and cash cards at the ATM, you can see that the development time of that decreased, and also the implementation and commercialization time of that decreased. So for new products that are potentially transformative, it originally took a long time for them to be discovered and deployed, and now it's taking a shorter time. Now, when we think about the next row or section in this graph, which is replacement products, and for example, energy and end-use customers, so the mobile phone, compact fluorescent light bulbs, lithium-ion rechargeable batteries, LCD TVs, and LED lighting. Again, these are consumer-facing products, and you could see that the implementation and the discovery and the development of that was relatively short because it's something that a consumer can buy. But then at the very bottom, when we look at energy generation technologies, we can see how long it takes, the number of years it takes to go from an invention, deployment, and demonstration to it actually becoming widespread, where with nuclear power taking 20 years, with combined gas cycle turbines taking 25, 30 years, solar photovoltaics taking even longer. And really, why is it that energy, something so crucial to what we have, is so difficult and takes so long to discover and deploy? And ideally, what we want to do is take those transformative technologies and shorten that bar graph. And the way we can do that is by using, potentially, artificial intelligence, robotics, and self-driving labs. This is another wonderful paper by economists at Stanford University. And what they looked at was essentially the research productivity over time with relation to the number of researchers. In economic theory, there's this broad assumption that the majority of economic papers look at the growth or productivity, or, for example, gross domestic product or GDP growth as a function of research productivity and the number of researchers. You multiply the two out. And a lot of people have kind of kept this idea that research productivity is constant. This paper analyzed a bunch of cases over a long period of time to show that actually that's not the case. Ideas are getting harder to find. We are spending more money, training more researchers, but the amount of research productivity is going down. And that may be a consequence of the fact that we're pushing frontiers further, or it may be a consequence of perhaps maybe the amount of data and the amount of processing that needs to happen can no longer be done without the aid of digital technologies. And so I wanted to explain, at least in my view, how innovation happens conceptually. You start with an idea and a hypothesis, then you develop a plan. And at least this is, of course, in the material science space. But then once you have that plan, you go synthesize that material, you make it. And then you process it. So that's either maybe you have to do something to it to make it better, or you have to incorporate it into a device. Then you take that and you characterize it. You test it in whatever environment needs to be, whether maybe it's a new battery material, so you test its cycling. Maybe it's a new catalyst, and you test how well it converts CO2 or produces hydrogen. And then, of course, there's data collection and analysis. Now, in academia does this all the time. Companies do this all the time. And traditionally, this loop can take anywhere from months to years, especially if it's material science-based. Ideally, you're lucky, if you're hopeful, that you get to a new material at the end. But sometimes that planning process can be a little bit random, can be a little bit sporadic, and may not necessarily be that informed or directed. And so is there a way that we could try to optimize this so that we can shorten this time frame and we can speed up innovation? So how can we do this? And I'm of the proponent that we are at a very exciting time in history where digital technologies, artificial intelligence, and what we can do in the digital realm is really unlocking new paradigms in discovery. And I can point to no better source than Moore's law, which, for those who aren't aware, is the law that there is an exponential doubling of the transistor count in microchips over time, which underpins the processing power of all computing. So basically what you're seeing here, and keep in mind that the left hand side there is an exponential curve. We're seeing exponential growth in the amount of processing power year over year over year, and it seems to be keeping up. So that means that we have an unprecedented access and amount of power that in our phones, for example, that spaceships, that the shuttles that brought people to the moon didn't even have. So what's really driving this idea of accelerating this loop is the amount of data, the big data that we now have access to, and the digital technologies that underpin that data, and also the automation and robotics that have come a very long way in a short amount of time. So where I see these two pieces really helping to accelerate this loop, for example, in robotics, to help to go from the synthesis portion to the processing portion, or from processing to characterization, automating that so that it is more robust, reproducible, and faster. And then on the artificial intelligence side of things, it's now thinking about, well, robots have been around for a while. There's things called computation or combinational chemistry, high throughput experiments. But what really is unique about it now in today's day and age is the massive advancement in the last 5-6 years in artificial intelligence, which is really a way to take a large amount of data and then using complex math and complex computer science techniques to then draw out correlations and descriptors in a complex set of data, reduce them into some sort of latent space that you can discover on, and then draw upon that predictions or interpolations that you may not have been able to do by manual analysis alone. And there it's really important to think about artificial intelligence and impacting the connection between characterization and performance evaluation or data collection analysis. And really it's to help look at that data in a multidimensional space that you may not be able to connect rationally, and it can find correlations that the human brain can't, and then suggest new compositions, new experiments, or new things to do in that loop. There are, of course, different levels of automation and different levels I think of when I talk about self-driving labs. The first that I wanted to describe is automated experimentation. And this of a use, for example, in pharmaceutical industry, in drug discovery, and it's really on the order of 100 to 1,000 in terms of sample production and characterization. And really what you're doing is you kind of have like a grid of, let's say, a different composition. I'll give an example in the next slide of a material that you want to discover, and you sequentially move along this grid in a brute force way and use robotics to synthesize the material and perhaps even test it. And so an example of this is shown in this, this little animation here. This was published in PNAS just this year. And what they're doing is they're using combinatorial design to discover new multi-metallic materials using robotics in an automated way. So what you're seeing is a robot that's depositing different inks of metal salts. And what it will do is these metal salts are different combinations of different elements. Platinum, palladium, rhenium, ruthenium, iridium, iron, cobalt, nickel, etc. In the field of fuel cell catalysis, the composition of the material is very important. And right now, fuel cells, primarily the highest activity and those that are commercial, use rare earth elements like iridium or ruthenium. It would be great if we could find materials that have a lower content of those rare earth metals, but still have the same activity or even better activity. It would be more sustainable, it'd be cheaper, and it'd be more scalable. So this project and this robot is trying to compose or synthesize a vast library of different catalysts at the same time, and of multi-metallic catalysts that are homogeneously dispersed, meaning that each of the different elements are not segregated, but are actually well mixed together. And it's doing this and then testing its characterization and its activity afterwards. Now, this project does not have any artificial intelligence. It's just high throughput experimentation. But already you can see that it can test in a much more reproducible and in a much faster way. For example, 88 samples, and it actually discovered a better material than industry standard. And I should mention that if you were to do this manually, it may take a skilled research scientist a day, maybe 2 days, to synthesize 2 or 3 samples, whereas this is doing 88 samples in a single go. The next level of automation, which we are in right now, and there's some really exciting companies that are focused on using artificial intelligence and design of experiments. ChemOS is an example of a company that was founded out of the University of Toronto, and they're doing some interesting stuff there. Citrine Informatics is another one too. But really what's happening here is, in addition to just the robotics, can we now include artificial intelligence and design of experiments? Rather than searching a grid in terms of, this is 5% this material and 10% this material, et cetera, and then going 5, 10, 15, 20, well, instead of doing that, can we use machine learning to intelligently determine what the composition of the material should be before it even makes it? And the idea here is, rather than searching along a grid, it optimizes within a certain space and finds the correct answer faster. It's really searching the space in an intelligent way. And artificial intelligence is really moving the needle in this regard. And a lot of that is with complex Bayesian optimization techniques and other advancements in that space that I won't go into detail with, but are certainly worthy of mentioning. And so here's an example of a robot. This was just published actually a couple of weeks ago. It's a mobile robot that is mixing and producing experiments in the lab, in a lab, by the way, which it free form roams in order to discover new materials to produce hydrogen at a cheaper, more cost-effective rate. And what's happening here is this robot, not only is it doing the synthesis portion of it, but it's also doing the characterization, the testing, and it's using all of that data to feed an AI algorithm, which then helps it determine the best material. So on the right-hand side, what you're seeing is a graph. On the left axis is hydrogen evolution, or the production of hydrogen. It's a measure of activity, how well this catalyst material is doing what it's supposed to do. On the bottom of the graph is the number of experiments from 0 to 700. And at the top of the graph is the number of days, from 1 to 8 days. In black are the controls. If this was if this robot was doing it without artificial intelligence, or it was only looking at, let's say, in a brute force way, or looking at only one sort of known or traditionally active composition, it would be at that rate. What's interesting is that even after, just immediately after the second day, it went from being sort of worse than the baseline to an order to 10 times higher than the baseline. And it's really interesting because what we're seeing here is that these 100 experiments that were done in a day in an automated way is 1,000 times faster than a human. And 683 samples were tested within this campaign of just 8 days. So, I mean, of course, I have to mention that, especially in today's climate with the pandemic happening, physical distancing going on, I'm sure industry and academics and a lot of people can look at this as an example of how we could try to continue productivity even in the face of these unprecedented times. And what's really interesting here is that the development of this project happened in 2 years. So in 2 years, they were able to go from essentially nothing into developing a mobile robot, a mobile lab scientist, essentially, self-driving robot. So it's extremely exciting, and these are really exciting times. However, there's this sort of fourth or third level of automation, which is really robotic discovery. Now, the examples that I've showed you so far are robots that are optimizing along a trajectory. And they're perhaps finding the best combination or the next best thing, but they aren't necessarily extrapolating beyond what their original constraints were. And they're not necessarily giving scientific intuition or discovery intelligence, right? So, and what the reason for that being is that robotics and data, it's really a matter of what is the data and what is the output. When a robot measures something, it doesn't necessarily have all of the context on what that something is. If it measures a material, it knows maybe its composition and its activity, but it won't know, for example, well, this is a platinum-based material, so chemistry would dictate that it has these number of electrons in this orbital. So human intuition would say that perhaps if we alloy this metal with another metal, this kind of activity would happen. We're close to that, but these self-driving labs are not yet there. And what I'm really excited about, and where the forefront of this is, and where a lot of folks are doing a lot of interesting work in this space, is actually combining the computational and quantum mechanical simulations with the artificial intelligence and the robotics in the loop. This is something that I have yet to see really be implemented at scale, but really it's about taking the hard part of discovery, which is the novelty and the newness and the scientific underlying physics and understanding, and incorporating that into the data processing, the artificial intelligence, and the robotics. So machine learning and ab initio simulations that bring more to science, more of the science into the data, and focuses more on extrapolation and correlation rather than just optimization. And to me, that's the exciting frontier here. It's how do you automate discovery? Now, I should mention that this effort has really exploded over the last few years and is around a term called materials acceleration platforms, which is really born out of a lot of work over the years in America and elsewhere in Europe around artificial intelligence, robotics, and materials discovery, but really crystallized under mission innovation, IC challenge, I believe it was 6, which is clean energy materials. And for those of you who aren't aware, Mission Innovation is an international organization and effort that was established in 2015 at the Paris, or may have been the Paris Climate Accord, but maybe at one of the climate conference of parties on climate change. And it was an organization of international, of countries around the world that committed to doubling their clean energy investment in R&D over 5 years. And they split that up into many different subtopics. One of them was in discovery of new clean energy materials. And born from that work, some fantastic work, was this concept of materials acceleration platforms. And what you're seeing on the screen right now are the variety and the location of these materials acceleration platforms around the world in things like additive manufacturing, or thermal conversion for thermoelectrics and energy storage, or organic electronics like in solar cells or organic lasers, CO2 conversion, hydrogen production, and battery design. So this is a movement. This is certainly an area where more and more people are getting into. And the reason for that is the cost of purchasing a robot and doing some computer science or even data management or AI has decreased so rapidly over the years for a few reasons. One, just the cost of buying a robot has decreased as this becomes more and more scaled, and the cost economics and unit economics of that improves. And then two, especially when it comes to digital technologies and artificial intelligence, the community has really come around the sense of open access, and there are so many tools available today that just build upon each other. And there's really an exponential effect, similar to how there's an exponential effect in, for example, Moore's law and computing power. There's now an exponential effect in discovery. And so what may seem like science fiction, these self-driving labs, these robotic arms that are doing experiments in the lab, are really becoming reality. And so here are a couple of examples of a few others that have been published recently. One is, for example, the first one is looking at carbon nanotube growth conditions. So using artificial intelligence and robotics to optimize and discover better growth conditions for carbon nanotubes, which can be used in a variety of applications as structural materials, as electronics, and consumer packaging, etc. The second, which is actually a Natural Resources Canada funded project with the University of British Columbia and the University of Toronto, called Project ADA, is looking at a materials acceleration platform for thin films for energy applications. And so those thin films could be things, for example, like smart windows, or perhaps LEDs, or et cetera. And the last one on the right is a robotic arm and a whole range of 3D printers. What they're trying to evaluate and use artificial intelligence and robotics and machine learning for is to look at the mechanical evaluation of 3D printed objects. Can we print different 3D objects, change their morphologies, and then see what is the optimal 3D printed shape or object for whatever particular application. I'm going to talk now a little bit about what's happening in Mississauga and what the NRC, why am I speaking about all these materials acceleration platforms and why am I so invested in them? Well, we're actually building a brand new national lab in Mississauga. This is going to be an innovation ecosystem hub to accelerate the development and commercialization of advanced materials. And its first real mission will be on energy materials, as it's part of the Energy Mining and Environment Research Center where I work in, and my program is a part of it. And it's located right across the street from Xerox Research Center Canada. There's actually a partnership with Xerox Research Center Canada around developing technologies in this space as well. And really, one of the exciting things about this is that we're actually going to be partnering with Natural Resources Canada, NRCan, CanMet Materials in Hamilton to build out a second and third floor that is dedicated to building materials acceleration platforms or MAPs. We're hoping that this becomes, at some point in its future, almost a user facility for industry, for academics, and for other folks to come on site and use these robotic self-driving labs to help them discover new materials in whatever application area they may see the most value in. This is sort of the initial laboratories and equipment for the first floor. There will, of course, be dedicated map rooms throughout. And I should mention that I am very excited for this to open up. Of course, I've been working from home because of the pandemic, but even before the pandemic, I've been working from home since I was hired at the NRC, so for about 1.5 years, because the construction on this, the building has been underway. So I personally am really invested and excited for this building to be up so I don't have to work from my living room anymore. But as I said, this idea of materials acceleration platforms, which we're partnering with Natural Resources Canada, and also have very strong collaboration with the University of British Columbia and the University of Toronto. A few professors there are kind of the pioneers in this space, very much so, at least in Canada. Professor Alana Spiro-Guzik, Professor Jason Hine, and Professor Curtis Burlingame, for example. And what we're trying to do is look at the synthesis, the characterization, the modeling, and all of this stuff, and put that together into and build these new self-driving labs. In the first 2 years, we're really looking at initial map development, and we're focusing actually on electrocatalysis. So producing water, splitting water, using renewable electricity, and then making hydrogen and oxygen with it. And we're hoping for a mature enough system for external users by the end of the second or third year. And really what we want is closed loop material design, on-site calibration, highly modular. These labs, maybe we'll have some self-driving robots that are mobile, like the video I showed before. Maybe we'll have them on platforms. But really it's about developing a center where we can develop this technology in Canada and become hopefully help to lead the innovation and the growth of this really new and exciting sector. So what's next? How the future of discovery will be impacted by the self-driving lab. These are questions and ideas and things I would like to muse about before I sort of take questions from the audience. And first, you know, I've given and I've heard talks like this throughout time, and there are a lot of people who think about these questions almost philosophically. For example, if we develop self-driving labs to do research, what is the role of the scientist? And I want to take this moment to explain that, at least in my opinion, the thing that these self-driving labs maybe can't do, and that's probably a little bit on the second question too, is the intuition and it's the creativity. We are trying very hard to improve self-driving labs and AI algorithms to think more and more like humans. But at the end of the day, it really is a tool, and it's not by any means expected to replace scientists, but rather help scientists accelerate the discovery and be an aid to them. I've had another, along this line, and this actually maybe goes to some of the presentations previously at CIC around education. You know, if we have these self-driving labs and graduate students around Canada are starting to use these self-driving labs, will we lose some of that richness of and the depth and detail in understanding exactly how to do a characterization or how to synthesize a specific material? Will that art and serendipity be lost? And that's a serious question, and something that I've been thinking about also. I think there's definitely room for both. Whereas this is a tool, we still have to be able to allow for that serendipitous discovery where, we've heard a lot of examples throughout history where some of the best discoveries were made from an accident. You can't necessarily, the whole point of self-driving labs is that we reduce the amount of accidents and that we can try to standardize these things. But we also need to find a way to have that natural serendipity be present in self-driving labs or in research in general. And more importantly, we need to think about how these labs are being used in academic spaces when we train the next generation of scientists. The role of automation and digitalization is large-reaching, and it's impacting every sector: manufacturing, finance, health, science, technology. It should be no exception to that. And it's my opinion that we should be preparing students for the next generation with marketable skills that they can then put to the marketplace. And quite frankly, coding, robotics, and digital technologies are the future in many, many ways. So what is the role of the scientist? The role of the scientist is to be creative, and the role of the scientist is to ask why, to focus less on the how and the doing, but to probe why this is happening, and to develop more of that innate curiosity that leads to serendipity and that leads to accidents of discovery. Now, what can't self-driving labs do? What I've showed you in terms of materials development is all very low technology readiness level, low TRL. It's at lab scale. It'll be very difficult, in my opinion, for self-driving labs to take technologies and scale them to the size that they need to be, and to work down that technology readiness pathway, that valley of death that I showed earlier, in a cost-effective way. Especially because today, at least, a lot of these self-driving labs are very specialized to the application that they're being developed for. So I think that the role of the self-driving lab is concentrated really in that discovery, the development, and maybe to the prototyping stage. But anything beyond that, we're still going to need scientists and engineers focused really on the larger system engineering, the balance of plant, and the integration of different components to make something industrially ready, to make a product. And one of the exciting things about this, though, is that it also allows for the folks who are working on components and system integration. It breaks down that barrier between the low TRL and sort of fundamental science and discovery with the mid TRL development, deployment, engineering. And you could think of these self-driving labs as really a bridge to those two worlds. Yeah, exactly. So what implications does this have for training the next generation of scientists? I explained that already. And I'm relatively young myself, and I had the wonderful opportunity during my PhD to do quantum mechanical calculations using dimensional functional theory, to go into the Canadian light source and being able to fire high-powered X-rays at catalyst materials to see how they work in real time, to doing artificial intelligence at, for example, Toyota Research Institute, and using that to discover batteries and fuel cells. And really what I hope that this does is it helps to diversify the training of the next generation of scientists, so that scientists can get a broader and more overarching understanding of the tools and techniques that underpin the discovery of our world. And the last topic that I also am very interested in discussing is what implications does this have on scientific equality? Equality is something that is very important to me personally, whether that be gender equality, diversity, visible minority equality, etc., but also a socio-economic equality. Now, when we think about discovery, and we think about all the great discoveries that have happened throughout time so far, it's really happening in advanced economies and developed economies in the Western world that have the resources and the technology to do so. And innovation is really one of the engines of economic growth. So in order for technologies to develop, it needs to have an ecosystem that will support that. Now, why I'm really excited about self-driving labs is because the cost reduction and the digitalization of many of these techniques means that we're going to hopefully see a democratization of discovery across the world. That labs in developing countries and developing economies that perhaps don't have the resources to invest in multi-million dollar labs can instead think about turning that into a smaller, more discrete package and automating that with self-driving labs and being able, because the cost of robotics is decreasing more and more and more. So I'm hopeful that not only will developing economies, developing countries have more access to tools of discovery through self-driving labs, but smaller companies do as well, which will lead to competition and ultimately growth. So I gave a very high level overview of self-driving labs, and in my opinion, the future of discovery. This is of course just one piece of the puzzle, and it's not the be all end all of what will come next. And I also described only a very, very, very small piece of the technology and the research that's being done across the world. But I hope it was a little bit of a taste into what we can expect. And I hope some of these questions, or some of the ideas and topics that I raised today leave you with some thought. And you think a little bit more about how to automate and digitize your research or even just your activities. The world, especially younger generations, are been born into a digital world. They are digital natives. And so really the barrier to do this kind of work is decreasing year on year. So I'm going to, I'll end up there, my presentation there, and maybe open up the floor for questions. Hopefully folks in today's talk found some of that interesting and have some questions they'd like to ask. So Keith, should I just go through the questions there, or would you like to ask on people's behalf? Oh, Keith, you're muted, by the way.
Thank you so much. So yeah, I can go through. There's two questions that are coming, a few of them that are coming in. So the first question would be, what is the minimum cost, you think, for establishing a self-driven lab to be manufacturing these lithium-ion batteries?
Oh, that's a really good question. Okay, so for lithium-ion batteries, it really depends on what piece of a lithium-ion battery that you want to look at. So are you developing the cathode material for it? Are you developing the electrolyte material for it? Are you doing a button cell and actually developing a specific stack? Or what's the scale or size you're looking at? For lithium-ion batteries, if you're focusing, for example, on the cathode material, most of which are carbon-based, then I actually think that the cost could be relatively low. One of these robotic arms can run anywhere from $10,000 to $15,000 to $20,000 per robotic arm, which may seem like a lot, but when you think about scientific instruments like a GC, a gas chromatographer, which measures different gas constituents in a given sample, those can run in the same ballpark and range. So I think what the question is what is the cost of, let's say, the hardware associated with building a self-driving lab? And that the biggest piece of that would be the robotic part of it. And there are many things that you can do. Robotics is becoming super cheap, and you know you can go on Google or on YouTube and find videos of amateur roboticists who are making cool robots doing silly things. So I would say that probably the cost all in to establish a lab is maybe around $30,000 to $40,000 to $50,000, and of course this depends on auxiliary equipment that you need for characterization or synthesis. You know, I don't think it's necessarily prohibitive today compared to what other research groups are doing and what research is working on. And what's indicative of that also is the fact that there's so many of these self-driving labs that are coming online just within the last couple of years.
All right, great, thank you. So there is another question from Oyin Kansola, where it's excellent talk, Phil. I wonder, what about the trade-off in using self-driving labs to accelerate discovery versus the loss of serendipity that you mentioned? Won't the gains in minimizing experimental cost, loss, and the process of troubleshooting give much more time for scientists to focus on analyzing and creatively interpreting the wealth of data they received, thus leading to even more creativity and far outweighing any loss of serendipity or any losses incurred by a lack of serendipity?
That's a good question, and to be honest, I don't have the answer to that. I mean, I think there is some literature out there around, especially around scientific economic theory and growth theory on how serendipity or how discovery is done. I think it's too early to tell with respect to self-driving labs what the tangible benefit is. There's definitely a observable benefit in terms of time and cost reduction, but in terms of discovery, I'm not quite sure. And again, I think this is we need to think about this as a tool. And while we're I firmly believe that by accelerating the process of discovery through self-driving labs, you're actually allowing for conditions of more serendipity to occur, just from a matter of sort of numeric statistics. The more experiments that happen, the more accidents that could happen, right? So overall, it's almost a rising tide lifts all boats analogy. But I think that, especially with discovery, the network effects that occur from a serendipitous discovery and the fact that many discoveries play in and interact with one another make it very difficult to quantify that. But that shouldn't mean that we should stop our efforts in self-driving labs. In fact, it's just evidence to me that we should accelerate those efforts.
I think one more question from Gail, where it says the traditional set of the traditional skill set, sorry, of a chemist doesn't typically involve AI or automation. And I think you touched on this question a little bit, but I think it's worth diving into more. It's, do you see chemists and material science updating and changing their skill set, or that this gap will be met by collaboration?
Both. I think both. Yeah. So I think that especially as, I mean, you can see even as early as elementary school and high school, where coding is becoming more and more part of the established curriculum. When we think about jobs in Canada, really we're a primary and tertiary industry economy, meaning we have a lot of natural resources, and we focus a lot on resource extraction, and then a lot of tertiary economy work, the service industry work, technology, digitalization, and even, for example, finance and banking, right? And there isn't really that much manufacturing anymore in Canada. There are pockets and niche areas, but not what it really used to be. So I think society as a whole is digitizing, and I think that regardless of if you think chemists need that experience or need to train today, it's going to happen naturally because students that go into the system will have some of that information and have some of those skills already. And it's really about being able to recognize that and be open to incorporating that into traditional chemistry disciplines, and to thinking about how, simple things from using coding to visualize data better, or even more complex things like thinking about developing descriptors around experimental data sets and finding correlations in that. These are all things that people can optimize their time with. And as someone who has done a lot of experiments, there's a lot of wasted time waiting for something to be finished, or waiting for something not working out, and waiting for a characterization tool to free up. So imagine instead if we could use that time, if chemists of the future, students and new scientists could use that time on digital efforts and technologies instead. Think about the productivity increases that could arise.
It's fantastic. So I think for today, if there is no more questions, we might take another moment just to thank Phil for his time today. Oh, we have one last question, if you do have the time, from Jasneet, of how can chemists and material science who have no background in AI really initiate this process?
Mm-hmm. That's a good question. I mean, I think that for chemists who have absolutely zero background in AI, okay, first I'll answer this by saying artificial intelligence has kind of become a huge buzzword. And a lot of folks are saying that they're doing AI when really they're kind of just doing advanced stats or not doing AI at all. So we have to be careful and cognizant about when we approach people who actually know about AI, that we understand the nuances between the differences within that field. Is it machine learning? Is it deep learning? Is it regression? Is it population? These are things that may seem like a nuance to someone who's not in the field, but could be completely different to those who are in the field. I would say that for chemists who want to get into AI, really there's a wealth of information out there on the basics of it. People have been trying to look at applying AI to finance and to healthcare for a very long time, and other fields of science as well. So it's about just getting a base understanding and seeing what's out there. And there's also a lot of good resources, sort of kits and tools and exercises that really, the application of artificial intelligence has never been easier. The development of it is extremely difficult, but the application of it is you can do artificial intelligence with 4 lines of code in scikit-learn or something like that. And you know, it's really about just getting in there, finding some use cases, applying those use cases to some of the data that you have, and then developing this slowly like that. But if you're a chemist and you want to get into this in a big way, then you should find an expert in the field. Ideally, someone that you can share a common set of a lexicon and understanding with, because I find that, especially in the hard sciences and computer sciences, the biggest barriers are actually just the words that they use, and a lack of communication understanding around the lexicon of those words. So there has to be an almost a translation between those 2 disciplines. But again, maybe I'm going on too long here. I would say just find some resources online to get your hands wet with them and start trying. And if that doesn't work, then reach out to someone you know or in an academic setting, and try to find someone who is working in that space, approach them, and then just have a discussion. At the very least, have a discussion.
Yeah, it's definitely great advice. So I think we have time for one last question, and there's 2 that kind of overlap, and it's looking at, could an over-reliance on automation and machine learning run the risk of the average science kind of losing their understanding of the fundamentals? And would that really matter in your opinion?
Oh, that's a good question. You know, this is a tough question because it's philosophical in a sense. Would it matter? To me, yes, absolutely. I think it absolutely matters. Especially when it comes to artificial intelligence, you'll hear the expression garbage in, garbage out. So if the data that you're giving the models is poor data, not grounded in reality, has no bearing on what you want to do, and is a mess, then the artificial intelligence of the self-driving lab will not be effective. So of course, the reason they call them fundamentals is they are the foundation. Scientists and engineers need that foundation in order to do things beyond that. Do I think it runs the risk of it? Yes and no, because it's my opinion that folks who are interested in machine learning or AI inherently are scientifically curious people. And there's, you know, a sense and a culture around the development of this space that there's a mutual respect around those who do method development and those who apply. So we need to think about that carefully and recognize that the fundamentals will always be necessary. And you know, do I think it may run the risk of some folks not investing enough time into the fundamentals? Yeah, for sure. But I think the gains and the folks who do this right, and I think the ones who don't invest in the fundamentals will realize very quickly that what they're doing isn't working, and they'll have to adjust. So I almost feel that the community and the technology and the discovery will self-correct for that.
Great, thank you for that response. So I think in the interest of time, we're gonna wrap up for today, and thank you one last time for all your great insights in this really interesting and emerging topic. With that, I would also like to flag everyone's attention to next week's talk, which is going to be saving solvents, and we're going to be welcoming Andrew Dix, as well as Leanna Smith and John Russell from the University of Toronto, and they're going to be talking a little bit about the environmental impacts of the recycling challenge of solvents, as well as discussing green chemistry. And as well, if you're enjoying these virtual sessions, we encourage you to join the CIC's in one of its constituent societies as a member. And as always, if you ever have any ideas for a virtual event or webinar, please contact us at the contact information on the screen. So with that, I just want to give one last round of virtual applause for Phil for this exceptionally interesting talk. And I hope everyone enjoys the rest of their day.
Thank you. Thank you so much. And if anyone has any questions or follow on, you can find me on LinkedIn. My email is plastered everywhere on the internet. Just Google me. Happy to continue this conversation. Thank you again for having me. And this is a wonderful venue and a great series. So thank you.
Great. Thank you again, Phil. Great. Goodbye, everyone.